I'd like to start in chapter 13, and that's an RC circuit. When we looked at inductance, so the voltage across the inductor would be equal to LdI dt, and we have the reactance for inductance is 2 pi f times L as a function of frequency, and the voltage across the inductor is always leading the current by plus 90 degrees. So if there's a current I that is a reference, the voltage is leading it by 90 degrees. It's very similar with a capacitance, an RC circuit. As soon as you close the switch here, let's say you have a DC voltage, you're charging up a capacitance to this resistance R. If I look at the current instantly, the current to the capacitor can change instantly, but not the voltage. The same thing with here. The current to the inductor cannot change instantly, but the voltage can. So it's the exact opposite. So there's a good analogy between both of them. If I look at the current, as soon as you close the switch, the voltage still be at 0. So all that voltage is going to appear across the resistor, and you have a very high current, which is called current rush. As the voltage is building up, when it reaches a steady state, and capacitor acts like a short circuit at a steady state, and all the voltage will appear across the capacitance at a steady state after 5 time constant. Now, if I look at, therefore, the current is actually leading the voltage, because as soon as this voltage is 0, the current is already at a maximum. So unlike the inductance, the current is leading the voltage by 90 degrees, or the voltage is actually lagging the current by 90 degrees. So that's a negative phase shift. So the reactance is exact opposite. It's 1 over. It's directly inversely proportional to the frequency. And instead of J, you have minus J to take out the 90 degrees phase shift. So the voltage is leading by plus 90 degrees, so we come up with a J to give you that plus 90 degrees. In capacitors, the voltage is lagging by 90 degrees, or what's minus 90 degrees phase shift, and that'll take the minus J. So minus J is down here. Let's do an example problem number 1. They give you an RC circuit. It's on pages 417. It says the component voltage is shown. So you have a simple RC circuit here. You measure the voltage with the voltmeters, and again, measure the RMS value for the voltage is 12 volts. The voltage across the resistor is 4 volts. We're taken using an AC voltmeter to determine the magnitude of phase angle of the voltage V of S. You use Kirchhoff voltage law, but that will be equal to the voltage across the resistor plus the voltage across the cap. But if I look at the current, the voltage across the resistor would be in phase with the current, but the voltage across the capacitance was lagging the current. Just like we did here, the voltage across the cap is always lagging the current by minus 90 degrees. So if this is 4, and this would be 12, and if I look at, I can draw a line here parallel to the voltage. Then the voltage V of S would be equal to voltage across the resistor plus the voltage across the capacitance. So that will give you 4 squared plus 12 square root of it. It'll give you 12.6, and this angle would be negative. This is my tangent inverse of minus 12 divided by 4, which is minus 71.56 degrees. Or you could just say the voltage V of S is equal to 4 plus minus J of 12. Okay, so the only thing is different now for the inductance is instead of plus J is minus J times 12. if I look at the series impedance for the RC circuit, again, resistance is not a function of frequency, it stays the same. Capacitance would be equal to, you replace it with minus J1 over 2 pi FC, and then the Z total would be equal to resistance plus the reactance of the cap, which is minus J times X of C, and X of C is equal to 1 over 2 pi FC. Then the total impedance would be equal to R squared plus X of C squared, and then an angle of theta would be equal to tangent inverse of minus, it's a negative, minus X of C divided by R. So the angle of the impedance would be negative phase shift. With the resistance that we had, the resistance and inductance, the RL circuit, the impedance angle was positive, and in a capacitive, the angle is negative. Let's take an example problem 13.7. It says calculate the value of Z total, I total, and V sub C1, V sub C2, and R, and the angle of theta for the circuit shown in figure 36A. They have two capacitors connected in series, 0.47 microfarads and 0.1 microfarads. R is equal to 1K. The resistance stayed the same. You want to calculate the reactance of each. You can combine the two capacitance, which would be 1 over C plus 1 plus 1. Since they're asking for the voltages for VC1 and VC2, they'll probably need to leave them in like that. So you calculate the reactances for each capacitor. 1 over 2 pi, 300 is the frequency, 0.47 times 10 to the minus 6 for the microfarads. That will give you 1.129 kilo ohms and 5.3 kilo ohm for C2. Then you put everything in phasors. This is 6 volt at angle of 0. You're going to take that as a reference. Minus J. Again, make sure you put a minus J in there to take so the negative phase shift. And then the 1 kilo ohms. Calculate Z total would be equal to 1K plus these two combined, and that gives you minus 6.42 kilo ohms. Then Z total would be equal to 1 squared plus 6.42 squared square root of it, tangent inverse of minus 6.42 divided by 1, and that gives you 6.5 K at angle of minus 81.2 degrees. That's Z total. And I total. Then, again, once you put everything into the phasors, the rest is just a matter of doing the calculation, just like you did with a DC. But again, you have to deal with a complex number. There's no need to memorize any equations. It's very straightforward calculations, as long as you can take out a phase angle and be able to do conversion from rectangle to polar, polar to rectangular conversion to simplify your circuit. I total would be equal to V divided by Z total. That's 6 divided by Z total. We took the voltage at a reference. And Z total is 6.5 K at angle of minus 81.2. 6 divided by 6.5 K, that gives you 9.923 milliamps. And then it's 0 minus the angle of the denominator. Minus minus will give you a plus. So you can see the current will be leading the voltage by 81 degrees because we took the voltage at angle of 0. Then once you calculate the I total, then the voltage across each cap here would be equal to whatever the current is multiplied by its reactance. But again, you need to take care of the minus J in there. Minus J is minus 90 degrees. Plus J is plus 90 degrees. So put it in phasors, and I total you already calculated. K and milli will cancel out. That gives you about 1.04 minus 90. When you multiply phasors, remember you add the phase angle, minus 90 plus 81.2, it gives you minus 0.8. Voltage across the cap 2 would be its impedance, reactance, which is 5.3 K at minus 90 times the current. And that gives you 4.9 and minus 8.8. So the both voltage would be in phase. And of course the voltage across the resistors is simply 1K times the current. And that gives you 0.923 volts. Milli and K will cancel out at angle of 81.2. But they ask for the angle theta. That's the theta for the impedance, and that was minus 81. 0.2. Now, again, once you put everything into phasors, then you can do the voltage divider rules that we did back in DC. The voltage across any component in a frequency domain would be equal to input voltage times the impedance for that component divided by the total impedance. We did the same thing. We said the voltage across R of N is equal to the input voltage times R of N divided by R total. So we're not doing anything different, except everything has to be done in a complex to make sure we take out the phase angle. Let's look at a frequency response of an RC circuit. Well, the frequency response is change in a circuit as a result of the change in the frequency. So if I look at this RC circuit, and you put a signal generator in here to change the frequency, you replace the capacitance with a minus J1 over 2 pi f times C, which gives you a minus JXC. At a low frequency, at DC, if you put 0 in here, 1 over 0, it gives you infinity, so it acts like an open circuit, so that there is no current flowing at a low frequency. At a high frequency, 1 over a very large number, it acts like a short circuit, and would be short circuited, the voltage would be equal to 0. So if I look at the voltage across the capacitance as a function of a frequency, if I vary a frequency here, at a 0 frequency there is no current flowing because the cap acts like an open circuit. If it's open circuit, there's no current flowing. So there's no voltage drop across the resistor. All the voltage from the input will appear across the capacitance. So you're right here. As you vary the frequency, higher frequency, lower reactance, and small impedance, so it gets smaller compared to the resistance R, so you have less voltage drop across the capacitance, you have more voltage across the resistor. And when extremely high, at high frequency, this acts like a short circuit, the voltage will be 0. At a frequency when the voltage is dropping, the voltage across the cap is dropping from the maximum voltage, which is when the frequency is 0, you have the maximum voltage, to 0.707. At that frequency, then gives you a bandwidth. So the RC circuit acts like a low-pass filter. It's passed at a low frequency, but it's blocking high frequency. And again, noise is a high frequency. If you have noise in your circuit, on your system, and your signal, you can put a simple RC circuit to block the high frequencies. And to determine the bandwidth then in omega would be equal to 1 over RC, or the frequency then would be 1 over 2 pi RC. So if you know the value of resistance in your capacitor, you can determine exactly what the frequency is. Then that gives you the bandwidth, and anything beyond that point will be blocked. You're losing, if the voltage is dropping to 0.707, if you square that, it gives you exactly 0.5. So that's what's also called a half power frequency. At this point, at that frequency, you're losing half of the power that you're putting in. You get half of it on the output. Now, if you look at the voltage across the resistor, at a low frequency, there's no current flowing, so all the voltage will appear across the capacitance. At a low frequency, this is 0. And you vary the high frequency, the inductor, the capacitor acts like a short circuit, and all the voltage will appear across the capacitance. Will appear across the resistance. And the same cutoff frequency, or the half power frequency. There are actually 3 different terminologies they use for that frequency. It's called half power frequency, cutoff frequency, or corner frequency. Those are all the same terminologies. At that frequency, then would be still be the same 1 over RC, and radians per second. That would give you the bandwidth. Anything above that, it reaches a steady state. So that if you take the output across the resistor, then the RC circuit acts like a high-pass filter. Now, let's look at the power calculations in an RC circuit. For the resistor in watts, the power again would be I square R. That's called the resistive power or the true power. P sub x is called the reactive power, which is in volt ampere reactive, is equal to I square x of C, but it has a minus 90 degrees phase shift. Then the apparent power will still be the same like we did with RL circuit. There's P sub R squared plus P sub x squared, square root of it. But the reactive power now is negative. So if this is P sub R, this is P sub x, it's a minus 90 degrees. And the angle now would be negative, and the apparent power would be at a negative phase angle. Now we talked about this before, so that the power factor, which is a number between 0 and 1, which is actually equal to the real power, the true power divided by apparent power, and they call that the power factor because as a factor you need to multiply the apparent power, which is voltage times the current, that's what it appears to be, in order to get the actual or the true or the real power. Again, this reactive power is not dissipating. That's a shuttle power that bounces back and forth from the source to the load, the part of the capacitive part of the load, and it does not dissipate. Half a cycle is you store it, and the next half a cycle we release it back to the source. Now, we talked about this in the past. We said if the power factor is dropping below 0.85, and then the power company, they adjust your bill accordingly. One of the reasons you can make the power factor corrections actually to increase this about 0.85 so you lower your electrical cost. And this is what we had before with the resistive power or the real power, and then this was P of X because most appliances, well not appliances, in the big industry, the furnaces or shopping centers, you always have a negative. The current is lagging the voltage, and it's called a lagging power factor, but if you look at the angle for the power triangle, this angle is positive. So in order to increase the power factor, get it close to 1, then you must lower the angle, because the smaller this angle is, the cosine of the smaller angle, it gets closer to 1. If it's 0, which is the case in a residential area, you'd always have the angle of 0. If you take a cosine of 0, it gives you 1, which is called the unity power factor. So you don't have to worry about adjusting the bill. But in order to increase the power factor, you must lower the angle. Well, if you have what is called inductive load, which is typical in case of like a simple motor, in order to lower the angle, then you need to lower, because this is a rated, let's say you have a 50 watt or 50 horsepower induction motor, let's say for pumping purposes in a well, then there's not much you can do. That's the rated power, so that's just going to stay the same. But you have a control over the reactive power. So if I lower the reactive power, then I'm lowering this angle, and that will be increasing the power factor. One way to do this, to add a capacitive, put an impeller with a load, is called power factor corrections. The negative, remember the reactive power for the capacitive is negative. So that will, if you add a negative to a positive, it will lower the reactive part of the power, and then that will result in a greater value of the power factor. And that's what they do. When you make a power factor correction, this is, let's say this is your motor, where there's a single phase or a 3-phase. Then you put a power factor, you put a capacitor in here. Single phase motors, they must put a capacitance. It's called starting capacitance. That's different than a power factor corrections. Sometimes the same one will kick in with a different value, but the 3-phase motors, they don't need starting capacitance because they always have a phase shift, and that's the advantage of a 3-phase motor. Not only there's no need for a starting capacitance, there's also has an advantage. It has less vibration with a three-phase as you do with a single phase. But if you're using a single phase type motor and you want to make a power factor corrections, then you put a capacitance and cross it other than the starting capacitance. And what that really does, it corrects the power factor. And to calculate the value of that capacitance, they use this equation. That's the power rating of your motor, tangent of the old theta, which is the old power factor, let's say is 0.7, and you want to increase it to, let's say, to 0.9, so that would be tangent of new theta, which is cosine inverse of 0.9, divided by omega, which is 2 pi times 60, in the case of 60 hertz, so 2 pi f. And this is the voltage rating. Let's say it's 120 volts. Motor just be V squared. So you can calculate what the capacitance value you need to put across the motor in order to make the power factor increase it, let's say, from 0.7 power factor into the 0.9 power factor. Let's look at an example, problem number 12. On pages 419, it says, refer to figure 1335B. It says calculate the value of resistance and reactive power for the circuit shown. So circuit 35B, they have 8 volt 8 volt source at a 250 frequency of 250 hertz. The capacitance is equal to 1 microfarad, and the resistance is equal to 750. So put everything in phasors. You need to calculate the reactance part. So it'll be minus jx of c minus j1 over 2 pi. Frequency is 250, and the capacitance is 1 microfarad, which is 1 times 10 to the minus 6. If you calculate that, it gives you 10 to the 6 divided by 250 times 2 pi, it gives you 1570.8. That will give you minus j 636.6 ohms. You calculate Z total, which is 750 square root of it, 750 square plus the impedance of the capacitance, which is 636.6 square root of it, and the tangent inverse of this negative number divided by 750. That gives you Z total. To calculate the value of the current, you take the input voltage divided by Z total. Since we're only looking at the magnitude of the power, then there's no need to calculate a phase angle. And that will give you 8.13 milliamps. And then you just calculate the real and the reactive power. The real power, with what we are reading, would be I squared, that's RMS, square times R would be 8.13 square times 10 to the minus 6, because if I square 10 to the minus 3, it gives you 10 to the minus 6 times 750. That gives you excuse me, 49.59 milliwatts. And then the reactive power would be I squared times x of c at an angle of minus 90 degrees. Again, be 8.13 times 10 to the minus 3 quantity squared times 636.6. That gives you 42.07 millivolt ampere reactive at angle of minus 90 degrees. And if you need to calculate the power factor, we cosine of the angle, and cosine of the angle of the impedance was minus 40.32. Take cosine of that, it gives you 0.67 power factor, and that's called a leading power factor. Leading and lagging power factor is referring to the angle of the current with respect to the voltage. So if it's a capacitive load, the current is leading. If it's inductive load, the current is lagging the input voltage, so that's called the lagging power factor. So leading power factor, it gives you a positive angle, negative angle. Lagging power factor, it gives you positive angle for the power factor, so it's exact opposite. Let's look at parallel RC circuit. And to do that, again, we can do an example, problem 27. It says calculate the impedance, current, and a power value for the circuit shown in figure 1341A. And 41A gives you 2 volts at 18 kilohertz frequency. It's cross a parallel combination of capacitive of 10 nanofarads and 1.5 k ohms. Given a frequency, they give it a capacitive value. You can convert everything into the frequency domain or phasors. Be minus j x of c minus j 1 over 2 pi times 18 times 10 to the 3, that's the frequency, times the value of c, which is 10 nanos 10 to the minus 9. Calculated, it gives you minus j 884 ohms. Put everything in the frequency, the resistance stays the same. Gives you 2 at angle of 0, and then the reactives minus j 884 and the voltage, which is 1500. Calculate Z total. It says calculate impedance, so which would be 2 are connected in parallel, the product or the sum, 1500 times minus j 884 divided by 1500 minus j 884. Minus j is minus 90 degrees, then the magnitude would be 1500 times 884. Convert this from rectangular to polar, it gives you 1500 squared plus 884 squared, square root of it, tangent inverse of minus 884 divided by 1500. If you carry that out, minus 90, this angle is negative, be like 40 some degrees. So minus 90, minus minus, it gives you a plus, then you end up with a minus 90 degrees, minus 59.52 degrees. And then multiply those two, divided by this number, it gives you 763.34. That's the magnitude of impedance in ohms. I total from the source would be the voltage divided by Z total. 2 at angle of 0 divided by 763.34 at angle minus 59.52. 2 divided by 763.34, it gives you 2.62 milliamps. 0 minus 59.52, it gives you 59.52. So you see the current is a positive phase shift, so the current is leading the voltage in capacitive circuit. To calculate the power values, the real power would be I squared times R. I is 2.62 milli times 10 to the minus 3 squared. The resistance is 1500. That gives you 2.65 milliwatts. And then the reactive power would be I squared times X of C at angle minus 90. So it would be negative 90 degrees phase shift compared to resistance power. And if you calculate it, it gives you 4.52 milli is volt ampere reactive. That's the units. And the angle is a minus 90 degrees. And last, we look at series RC, parallel RC, and then you can also have a combination of series parallel circuit. We did the same thing in an inductive circuit. We did it also back in chapter 4 and 5 with a resistive load. So to do that, let's work on an example. Problem 33 says, it's on pages 421. It says calculate the component voltage and currents value for the circuits shown in figure 1343A. You got 150 ohms connected in a parallel combination, 1 microfarad and 1 kilo ohms. Again, I'm pretty sure it's clear now that you cannot combine this. Either they do it in parallel. You cannot say it's 1 microfarad times 1 kilo ohm divided by 1 microfarad plus 1 kilo. They're completely two different animals. This is very sensitive to the frequency. This one is not a function of a frequency. This one will amplify the current, and this one will differentiate or negate, depends on the capacitive or inductive load. So that you cannot do. But we have to put it in a frequency domain. once you put in the frequency domain, then this will be product over the sum in phasors, you can convert it into the impedances. And then you add it to 150. That gives you the total impedance, and then you take the voltage divided by the total impedance to give the current. Once the current comes in here, then you can do the current divider rule to determine the current to each load. Alright, that's pretty much everything in that chapter. We got to look at a set of problems in chapter 13. Problem 8, 11, 19, 23, 28, 34, 39, and 40. And we'll stop here. Next time we'll look at those problems. And we'll look at problem 33 also. All right.